Consider a simple pendulum swinging back and forth under gravity. Its position at any instant can be denoted by an angular displacement theta. This is an example of a mechanical system. Now consider an inductor-capacitor or LC circuit. I of t is the current flows through this circuit. This is an example for an electrical system. Do you know both of these different systems can be described by the same rule? It's called a principle of stationary action. In this video, I will explain what this principle means. Before explaining the principle, we first need to understand a concept called action. In both mechanical and electrical systems, two kinds of energy are involved, one associated with motion and other with position. For a simple pendulum, these are kinetic and potential energies, while for an LC circuit, they are magnetic and electrical energy. If you take the difference between these two energies, you will get a new quantity called a Lagrangian. For the simple pendulum, the Lagrangian is defined as the difference between kinetic and potential energy of the system. Here is the expression for pendulum's Lagrangian, where theta is the angular displacement, L and m are length and mass of the pendulum. In the case of the LC circuit, the Lagrangian is defined as the difference between magnetic energy and electrical energy. Its expression looks like this, where Q is the charge, L is the inductance, and C is the capacitance of the system. For the simple pendulum, the Lagrangian is a function of the angular displacement theta, its time derivative theta dot, and time. In the case of the LC circuit, it depends on the charge Q, its time derivative Q dot, and time. These quantities theta and Q are called generalized coordinates, while their time derivatives theta dot and Q dot are called generalized velocities. Thus, we can say that a Lagrangian is a function of system's generalized coordinate, generalized velocity, and time. Once we know the Lagrangian of a system, we can calculate a quantity called action. It's obtained by integrating the Lagrangian over time along a particular path. This definition of action is called Hamilton's action. We defined Lagrangian and then introduced Hamilton's action. Now we need one more essential ingredient to understand the principle of stationary action, and that is the concept of path. For the simple pendulum, path is a function theta of t, describing how the angular displacement changes with time. For the LC circuit, path describes how charge evolves over time. We can represent a path like this by plotting the generalized coordinate of the system versus time. This is called configuration space diagram. Both theta of t and q of t are the continuous curve in the configuration space. Path is a set of values for generalized coordinate can take. It's a continuous curve in the configuration space. Is there only one path a system can take? The answer is no. Q1 of t, Q2 of t are the other possible paths. There are infinitely many possible paths for a system. For every possible path, we calculate this integral value. Thus, we will get action for each path. Nature chooses one special path. Let's suppose Q1 is that special path. The action integral value along this path is denoted by S of Q1. Now imagine a small variation delta Q in this path and creating a new nearby path. The action along this slightly varied path is S of Q1 plus delta Q. The first order difference between these two action values is 0. In fact, the first order change between S of Q1 and the action values for all nearby paths is 0. We can say at this special path, the action is stationary. Out of all possible paths, the system follows one path where the action is stationary. This is known as principle of stationary action.